So, Max, I was trying to read this massive technical document last night, and I swear my brain just shut down halfway through.
Let me guess, you hit that cognitive wall where you couldn't keep track of all the context anymore?
Exactly. And it got me thinking, if I'm struggling with this, imagine what language models must go through with their fixed context windows.
Well, that's actually perfect timing because today's paper tackles exactly that problem.
Welcome to another episode of Totally Unprofessional Peer Review. I'm Casey Park, your developer host who's obsessed with structure and flow.
And I'm Max Stone, bringing you the theoretical perspective with a focus on metrics and methodology.
Today, we're diving into a fascinating paper titled Recursive Language Models that proposes a novel approach to handling arbitrarily long prompts.
This paper introduces what they call Recursive Language Models, or RLMs, which essentially allow language models to break down massive prompts into manageable chunks and process them programmatically.
What's really interesting is that these RLMs can handle inputs up to 2 orders of magnitude beyond typical model context windows. We're talking about processing text that would normally be way too long for standard models.
And they're not just handling longer text, they're actually outperforming both base language models and other long context approaches across diverse tasks, often at comparable or even lower costs.
It's like teaching an AI to use a notepad and recursive thinking instead of just trying to remember everything at once.
Exactly. And what's particularly clever about this approach is how it treats long prompts as part of an external environment that the model can interact with, rather than something it needs to process all at once.
So stick around as we unpack how these recursive language models work, analyze their performance compared to traditional approaches, and explore how they interact with their text environment.
And if you've ever wondered how we might get AI to read and understand entire books or code bases without breaking the bank or melting processors, this episode might just have your answer.
Let's dive deeper into what makes recursive language models so innovative. At its core, this approach completely rethinks how we handle long text with language models.
Exactly. The traditional approach has always been to try cramming as much text as possible into a model's context window, essentially trying to make the model remember everything at once.
Which is kind of like me trying to read that entire technical document in one sitting. Not very effective.
Right. The key insight from this paper is that long prompts shouldn't be fed directly into the neural network. Instead, they should be treated as part of an external environment that the language model can interact with.
That's a paradigm shift. So instead of saying, here's a 50-page document, please analyze it all at once, it's more like giving the model tools to explore the document on its own terms.
Precisely. The authors draw inspiration from what are called out-of-core algorithms, systems with small but fast main memory that can process much larger datasets by cleverly managing how data is fetched into memory.
That's a concept developers are familiar with. It's like how databases handle queries on terabytes of data without loading everything into RAM at once.
Let's look at how this actually works in practice. The paper provides a great diagram that illustrates the process.
This diagram really helps visualize the concept. So what we're seeing is that the RLM loads the input prompt as a variable inside a Python REPL environment, which is basically an interactive programming environment.
Exactly. Notice how on the left side, the entire prompt is loaded as a variable in this environment. Then the language model can write code to examine parts of it, split it up, and even call itself recursively on specific sections of the text.
I see that in the middle of the diagram, it's using Python code to split the text by chapter markers and then making recursive calls to process each relevant section. That's really clever.
And on the right side, you can see these recursive calls in action. The model is asking sub-questions about specific chapters or sections, essentially breaking down the large problem into manageable chunks.
Let's take another look at this diagram. What's particularly interesting is how the model is actually writing code to help it process the text. It's using print statements to examine parts of the text and split functions to break it into manageable pieces.
And what's really powerful here is that this approach tackles a fundamental limitation in previous methods. Earlier approaches focused on recursive decomposition of tasks, but the input itself still couldn't scale beyond the context window of the underlying language model.
Right, because in this case, The entire text isn't being loaded into the model's context window at all, it's in an external environment that the model can programmatically interact with.
The paper makes an interesting point about context windows too. They hypothesize that the effective context window of a language model can't be understood independently of the specific task.
What do they mean by that?
They're suggesting that more complex problems will show performance degradation at shorter lengths than simpler ones. So the useful context length isn't just a fixed number, it depends on what you're asking the model to do.
That makes sense. It's like how I can remember a list of 10 simple words easily, but might struggle with 5 complex mathematical concepts.
Exactly. And this is where the recursive approach really shines. By breaking down complex tasks into simpler subtasks, it can effectively handle much longer inputs than would otherwise be possible.
So in their implementation, they're using a Python REPL environment. The paper mentions they use GPT-5 Mini for the recursive calls and GPT-5 for the root language model. That seems like a smart optimization for balancing capability and cost.
It is. And they also did an interesting ablation study where they removed the ability to make subcalls. In that case, the model could still interact with its context in the REPL environment before providing a final answer, but couldn't recursively call itself.
That would help isolate exactly how much benefit comes from the recursive calling versus just having programmatic access to the text.
One thing I found particularly impressive is that RLMs can scale to the 10 million token regime. That's orders of magnitude beyond what traditional approaches can handle.
To put that in perspective for our listeners, that's roughly equivalent to a 3,000-page book. And they're saying RLMs can outperform base language models and existing scaffolds on these massive inputs by up to twice the performance.
While maintaining comparable or even cheaper token costs, which is crucial for practical applications.
Are there any downsides to this approach?
The paper does note that RLM performance is slightly worse on smaller input lengths, suggesting there's a trade-off point where it makes sense to switch from a base language model to an RLM.
That makes sense. There's probably some overhead to setting up the recursive structure that isn't worth it for shorter texts.
Another interesting aspect is that RLMs are model agnostic, meaning this inference strategy can work with different underlying language models. But different models will exhibit different decisions on how they manage context and make subcalls.
So the core innovation here is that all context window management is handled by the language model itself, rather than being predetermined by the system architecture.
Exactly. The model decides how to break down the text, what parts to examine in detail, and when to make recursive calls, all based on the specific task at hand.
This reminds me of other recent work like Walking Down the Memory Maze and Thread, thinking deeper with recursive spawning that the paper references. It seems like there's a growing recognition that we need more sophisticated approaches to handling long contexts.
Definitely. And what sets RLMs apart is that they can produce essentially unbounded tokens well beyond the limit of the base language model by returning variables in the REPL as output.
So, the RLM can iteratively construct these variables as a mixture of programmatic and submodel output calls, effectively building up a response of any length.
It's a really elegant solution to a fundamental limitation of current language models.
Now let's talk about what really matters, the performance. How well do these recursive language models actually work compared to traditional approaches?
That's where things get really interesting. The paper includes some compelling data showing that RLMs dramatically outperform both base language models and other long context approaches across diverse tasks.
Let's look at some of the graphs they included. This one is particularly telling.
This is a great visualization. On the left, we see GPT-5's performance, and on the right, we see the RLM version using the same GPT-5 model. The x-axis shows input context length on a logarithmic scale, going from 8K all the way up to 1 million tokens.
And those 3 different lines represent different tasks, right? SNIAH, O-long, and O-long pairs?
Exactly. These tasks represent increasing levels of complexity. SNIAH is a needle in the haystack task where you need to find a specific piece of information in a large text. OOO long requires examining and transforming chunks of input semantically, then aggregating them. And OOO plagues requiring pairwise reasoning.
What jumps out at me is how quickly the performance of GPT-5 degrades as the context length increases, especially for the more complex tasks. For OLOG pairs, it drops to nearly 0% by the time you hit 30K tokens.
Right, and notice the red shaded area on the left graph. That represents input lengths beyond GPT-5's context window of 272K tokens. The base model simply can't handle inputs that large.
But look at the RLM version on the right. The performance degrades much more slowly, and it can handle inputs well beyond the base model's context window, all the way up to 1 million tokens.
The paper calls this phenomenon context rot, where the quality of even frontier models like GPT-5 degrades quickly as context gets longer. But RLMs maintain much stronger performance across the board.
I'm also interested in the specific benchmarks they used. The paper mentions they evaluated RLMs using both a frontier closed model, GPT-5, and a frontier open model, Quentry-Coder 480B.
Yes, and they tested across 4 diverse tasks with varying levels of complexity. Let's look at the detailed performance comparison table they included.
This table is packed with information. We can see they compared base models, CodeAct with BM25, a summary agent approach, the full RLM, and an ablated RLM without subcalls.
And across 4 different tasks, Code QA, BrowseCom Plus, 00000, and 0000. Pairs. Look at the task lengths at the top. Code QA ranges from 23K to 42M tokens, and BrowseCom Plus is a massive 6M to 11M tokens.
The asterisks are telling too. They indicate runs where the method hit input context limits. The base models couldn't even attempt BrowseCom Plus because it's way beyond their context windows.
What I find most impressive is the 000 pairs results. The base model scored essentially 0.04% for GPT-5 and 0.6% for Quentry-Coder. But the RLM version scored 58% and 23 first, respectively. That's a massive improvement.
The paper calls this an emergent capabilities. The RLM approach enables these models to handle extremely information-dense tasks that the base models completely fail at.
And on BrowseCom Play, which has those massive 6-11M token inputs, RLM with GPT-5 scored 91.33%, outperforming both the summarization and retrieval baselines by over 29%.
But what about cost? These performance gains are impressive, but are they practical from a cost perspective?
That's where it gets even more interesting. Let's look at their cost analysis chart.
This chart shows the cost distribution at different percentiles, the 25th, 50th, 75th, and 95th percentiles of total API costs for each approach.
What's remarkable is that at the median 50th percentile, RLMs have comparable or even lower costs than the base models. For GPT-5 specifically, the median RLM run is actually cheaper than the median base model run.
But there's a catch. Look at those 95th percentile costs. Some RLM runs can get significantly more expensive than the base model approaches.
Right, the paper notes that RLM costs have high variance due to differences in trajectory lengths. Some complex queries might require many recursive calls, driving up the cost.
But compared to the summarization baseline, which has to ingest the entire input context, RLMs are up to 3 times cheaper while maintaining stronger performance. That's because the model can selectively view only the relevant parts of the context.
On BrowseCom Plus, the paper mentions that the cost of GPT-5 Mini ingesting those massive 6-11M input tokens would be 1.50 to 2.75, while RLM with GPT-5 had an average cost of just 0.99.
So to summarize the performance analysis, RLMs dramatically outperform base models and other long context approaches, especially as context length increases and task complexity grows.
And they can handle inputs up to 2 orders of magnitude beyond typical model context windows. We're talking millions of tokens here.
All while maintaining comparable or even lower costs at the median, though with some potential for higher costs in complex cases.
The paper also notes an interesting difference between the 2 frontier models they tested. While both GPT-5 and Quentry-Coder showed strong performance as RLMs relative to their base versions, they exhibited different behaviors across tasks.
Right, on BrowseComp, plus specifically, RLM with GPT-5 nearly solved all tasks, while RLM with QuentFreeCoder struggled to solve half of them. So the underlying model quality still matters a lot.
Another interesting finding was the ablation study, where they removed the ability to make subcalls. Across all information-dense tasks, full RLMs outperformed this ablated version by 10% to 59%.
That really highlights how crucial the recursive calling capability is to the overall approach. It's not just about having programmatic access to the text, it's about being able to break problems down recursively.
Exactly. The recursive approach allows the model to handle complex tasks by breaking them down into simpler subtasks, which is especially valuable as input lengths grow and tasks become more information dense.
So, the takeaway here is that RLMs represent a significant advancement in handling long contexts. They scale better, perform better, and often cost less than traditional approaches, especially for complex tasks with very long inputs.
And they do this while remaining task agnostic. The same RLM approach works well across diverse tasks from code understanding to information retrieval to complex reasoning.
Though the paper does note that the optimal mechanism for implementing RLMs remains underexplored, so there's likely room for even further improvements in the future.
Absolutely. This feels like an important step forward in addressing one of the fundamental limitations of current language models, their ability to effectively process and reason over very long contexts.
Now let's dive into what I find most fascinating about recursive language models, how they actually interact with their environment to process these massive texts.
This is really the heart of what makes RLMs so innovative. The paper describes it as treating long prompts as part of an external environment that the language model can programmatically examine, decompose, and recursively call itself over.
Let's take a closer look at this diagram again to really understand how this works.
So what we're seeing here is that the RLM doesn't try to directly process the entire prompt. Instead, it loads the prompt as a variable in a Python REPL, which is basically an interactive programming environment where you can execute code line by line.
And that's crucial because it means the model isn't limited by its fixed context window. The prompt exists in this external environment, and the model can write code to selectively access and process parts of it.
Exactly. Look at how in the middle section the model is writing actual Python code to interact with the text. It's using print statements to examine snippets, split functions to break the text into manageable chunks, and most importantly, it's making recursive calls to process specific sections.
As a developer, this approach makes so much sense to me. It's like the difference between trying to read an entire codebase at once versus using tools like grep or find to locate and focus on just the relevant parts.
That's a great analogy. And what's particularly clever is that the model itself is deciding how to break down the problem. It's not following some predefined chunking strategy.
Let's look at some of the specific strategies RLMs use when interacting with their environment. The paper identifies several key patterns.
This figure shows three main interaction patterns. In panel AA, we can see RLMs using code to interact with, probe, and filter their context.
Look at that code. It's defining a function called find snippets that uses regex to search for keywords in the context. It's creating a sliding window to scan through the text and find relevant sections without having to process the entire document.
And what's fascinating is that the paper observed RLMs using model priors to guide these searches. For example, they saw RLMs searching not just for keywords explicitly mentioned in the prompt, but also for related terms the model has prior knowledge about.
In panel B, we can see another key strategy, deferring reasoning over large contexts by making recursive LM calls.
This is where the recursive nature of RLMs really shines. Instead of trying to process everything at once, the model breaks down complex tasks into simpler subtasks and calls itself recursively to handle each one.
In this example, it's processing a batch of questions by calling the language model for each individual question. This divide and conquer approach is much more efficient than trying to answer all questions in a single pass.
And finally, in panel C, we see how RLMs can stitch together outputs from recursive calls to form longer composite outputs.
And this is particularly important for tasks that require aggregating information from different parts of the input. The model can process each part separately and then combine the results programmatically.
The paper mentions that this was especially useful for the OOOOOO chi pairs task, where the model needed to find and process pairs of related information from different parts of the text.
What I find particularly interesting is how the RLM approach allows models to produce outputs that are essentially unbounded in length. Since the outputs can be built up iteratively in the REPL environment, they're not constrained by the model's output token limit.
That's a great point. The paper specifically mentions that RLMs can produce unbounded tokens well beyond the limit of the base language model by returning variables in the REPL as output.
Let's talk about some of the specific strategies the researchers observed RLMs using in their experiments.
One common pattern they saw was RLMs using regex queries to search for chunks containing keywords from the original prompt or phrases the model had prior knowledge about.
They also observed RLMs probing the context by printing a few lines to get a sense of the content and then filtering based on those observations.
Another interesting strategy was answer verification through sub-LM calls with small contexts. The RLMs would make recursive calls to verify their answers, which helps avoid context rot by using sub-LMs with smaller, more focused contexts.
That's a smart approach. By breaking down the verification into smaller subtasks, the model can maintain high accuracy even for complex problems.
The paper also mentions that the choice of decomposition can greatly affect task performance, especially for information-dense problems. Different ways of breaking down the input can lead to very different results.
That makes sense. As any developer knows, the way you structure a problem can have a huge impact on how efficiently you can solve it.
One thing I found particularly interesting was the ablation study they did where they removed the ability to make subcalls. The model could still interact with its context in the REPL environment, but couldn't recursively call itself.
And what did they find?
They found that on information-dense tasks like OOOOOOOOOO pairs, the full RLM with recursive calling capabilities outperformed the ablated version by 10% to 59%. This suggests that the recursive calling is crucial for these complex tasks.
Let's take another look at that figure showing the different interaction patterns. What strikes me is how the RLM is essentially writing its own code to solve the problem. It's not following some predefined algorithm.
That's a key insight. The paper emphasizes that all context window management is handled by the language model itself, rather than being predetermined by the system architecture.
And that's what makes this approach so flexible and powerful. The model can adapt its strategy based on the specific task and input, using different techniques for different situations.
The paper also notes that they focused on synchronous subcalls inside a Python REPL environment, but suggests that alternative strategies involving asynchronous subcalls and sandboxed REPLs could potentially reduce the runtime and inference cost even further.
That's an interesting direction for future work. Asynchronous processing could allow multiple subtasks to be handled in parallel, which could significantly speed up the overall process.
The authors also cite related work like self-steering language models and large language model-based multi-agents, suggesting that this approach fits into a broader trend of giving language models more agency and tools to solve complex problems.
It reminds me of tools like OpenAI's Codex CLI and Deep Research, which also involve language models interacting with external environments to accomplish tasks.
Absolutely. There's also MemGPT, which treats LLMs as operating systems with persistent memory and the ability to execute code.
So to summarize this section, RLMs interact with their environment by treating long prompts as external variables that they can programmatically examine and manipulate.
They use strategies like regex filtering to find relevant information, recursive calling to break down complex tasks, and output stitching to combine results from different subtasks.
And this approach allows them to process inputs far beyond their normal context windows while maintaining high performance and reasonable costs.
It's a simple but powerful idea. Instead of trying to cram everything into the model's context window, give it tools to interact with and explore its environment in a more natural and efficient way.
Which is exactly how humans handle large amounts of information too. We don't try to memorize entire books. We flip back and forth, take notes, and focus on the most relevant sections.
And that brings us to our next section, where we'll wrap up our discussion and consider the broader implications of this research for the future of language models. So there you have it. Recursive language models represent a fundamental shift in how we approach context length limitations. Instead of just trying to build bigger and bigger models, RLMs give models the tools to intelligently navigate and process massive amounts of information.
Exactly. It's like the difference between trying to memorize an entire library versus knowing how to use the card catalog and skim through books efficiently. This approach could revolutionize how AI systems handle everything from massive code bases to entire books or legal documents.
And the performance gains are truly impressive, especially for those complex, information-dense tasks that traditional models struggle with. I'm particularly excited to see how this approach evolves as researchers explore asynchronous processing and other optimizations.
Thanks for joining us for another episode of Totally Unprofessional Peer Review. If you enjoyed this breakdown, don't forget to subscribe and leave us a review.
And remember, if your AI keeps hitting its context window limit, don't just give it more memory, teach it how to take notes.